All right. All right, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions. Or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to Dr. Francesco Romer, who is a postdoctoral researcher in the Numerical Mathematics and Scientific Computing Group at the Weierstrass Institute for Applied Analysis and Stochastics in Berlin, Germany. He received his PhD in 2023 in mathematical analysis, modeling, and applications from the International School of Advanced Studies in Trieste, Italy. His thesis, supervised by Professor Gianluigi Rosa and Professor Giovanni Stabile, focused on the nonlinear parameter space and model order reductions enhanced by scientific machine learning. Today, Francesco will talk about intrusive model order reduction of parametric PDEs using neural networks, approximants of the solution manifold, and adaptive hyperreductions. I'm sure we are going to hear a wonderful talk from Francesco. Now let me ask a question to Francesco just to get to know him better. Here you go. Okay, I happen to know that you are passionate about dancing.
Yeah.
What kind of dancing do you like to do? And if you can describe what it is and how it works briefly, that would be awesome.
Okay. Well, I started years ago, even before COVID, to dance Lindy Hop, also here in Europe. And yeah, it's a very lovely environment and a way to distance yourself from coding and math, let's say. And it's more focused work job. Yeah, I guess everybody knows at least what Lindy Hop is, but yeah, I guess
Except
it's
me.
well, yeah. But yeah, I mean, I suggest you to look into it into YouTube. I don't know, or yeah.
I will do so, definitely. Yes, yes. You increased my curiosity about that. Great. The stage is yours.
Thank you. Thank you for the introduction. And so I will present a work I've done during my PhD studies at CISA in collaboration with Giovanni Stabile and Gianluigi Rozzo. The work is about an extension of the hyperreduction of the nonlinear manifold method. And before introducing it, I will present some motivations behind the new methodology. So I'll introduce the nonlinear manifold method starting from the finite element, passing through the reduced basis method. So if you have in mind the most simple PDE, like the Poisson problem, you can write the weak formulation in this way. And you can discretize it in space and choose your discretization method of choice, for example, the finite element method. In this case, your answer space would be the space of continuous functions that are restricted locally to the elements of the triangulation are polynomial of degree k. But you could also choose a spectral global basis of orthonormal functions on the whole domain if the domain is nice. And but what about if you have additional parameters on your PDE for which you have to find solutions? And these parameters may affect the geometry of your computational domain or enter as diffusion parameters in your weak formulation or in your source term. Well, in this case, you could exploit some solution you have computed beforehand in a so-called training stage to tailor a specific answer space for this problem to infer new solutions corresponding to parameters you have not seen yet. And this is a lot, as many relationship with the using this spectral basis method on the whole domain. Instead, in this case, we would use a much smaller dimensionality reduced basis. So still linear basis, but tailored for your problem. So this is more or less the nomenclature of model reduction. So you want to find solution UH for this weak formulation, and you introduce a parameter space K to which your parameter mu belongs to. The solution map L from that maps each parameter to its solution. The solution manifold, which is the image of the parameter space through the solution map. And in a training stage, usually collect is called snapshot matrix. So for different parametric instances from 1 to n train, their respective solutions. Once you've done this, you consider the same weak formulation, but instead as answer space, you want to find your solution as linear combination of a few number of modes, let's say R, with R very small with respect to the full dimensionality of your state space. And this linear combination is made with a vector on the global base in relation, also with a lot of analogies with the spectral basis method on the ball domain. But in this case, the elements of your basis will come from a singular value decomposition of your snapshot matrix. And of course, the idea behind model reduction is that you amortize the cost of computing additional and training snapshot in order to infer efficiently new solution at the prediction or online stage. But of course, this sometimes is not sufficient to approximate accurately a solution, because in model reduction, usually you sacrifice accuracy in favor of computation, a smaller computational cost. But in some cases, this is not enough, and you need approximants which are not linear in a sense. So I will present today how you can use as answer space nonlinear mappings, so a nonlinear answer space for your solution, and how you can solve for a solution in an efficient way. In this case, for example, you can consider as answer space the image through a nonlinear map phi instead of a linear map from an open set in the ambient space of dimensionality R, with R still very smaller with respect to the full dimensionality of your state space. And of course, the problems of using a linear reduced basis is very well known in the literature, and can be explained simply with looking at the model reduction of a scalar linear transport problem. So in this case, the initial condition is 0, and you have a left boundary condition equal to 1. So basically, the solution, if you consider standard discretization, is 1 followed by zeros, so it is continuous. And at the next time instant will be 1, 1 followed by 0, 1, 1, 1 followed by 0. If you assemble the snapshot matrix where the columns correspond to your solutions at different time instances, in this case, time is the only parameter, and then you evaluate the eigenmodes with the SVD, you can then plot the residual energy of your system, and you can see that even with different levels of discretization from more or less 100 to 2000, you can see that you need more than the 80% of your modes to retain more than 95% of the energy of the system. This in comparison to, for example, the incompressible Navier-Stokes equations, so a typical benchmark flow past a cylinder, implemented in the caffeinated volume inside the OpenFOAM. And you would see that you would need less than 5% of your eigenfunction of the eigenmodes to retain more than 95% of the energy of the whole system. So even if it's a more complex problem to solve, it's more easy to reduce with the reduced basis method in this sense. And a lot of practical applications have this problem. And to be more quantitative, it's in the concept of Kolmogorov and width is introduced. So you consider a parameter space K subcompass subset of a parameter space calligraphic P, and you can find the Kolmogorov and width for a fixed dimensionality n of your linear approximation space as the best approximation error uniform with respect to the solution manifold. And the Kolmogorov width has been evaluated for its asymptotic decay has been evaluated in many studies. And you can see that even for the incompressible Navier-Stokes equations using considering as parameter the source term itself as a function, you have almost exponential decay, minus n, 1 1 divided by 3 times some constants. And also the famous case for linear recursive problems of exponential decay, but also more difficult to prove for solution maps which are holomorphic. You can find approximations, asymptotic estimates like this. So for a parameter mu, which is a function of regularity S, you have this kind of estimates. And of course, for the linear evaluation problem I presented before, but also with equation, you would have instead a lower bound of n to the -1/2. This strictly depends also on the initial conditions. So it's important to notice that not every advection dominated problem has this kind of slow Kolmogorov with decay. In fact, a lot depends on the regularity of the initial conditions and also on the regularity of the parameter to solution map. And more generally, also it may happen that in practical applications, even if you have asymptotically slow Kolmogorov with decay, you may still reach a sufficient accuracy with a sufficiently small number of modes. So it does not mean that if you have a very slow Kolmogorov decay, then you cannot approximate your problem at all. It depends case by case. Yeah, and also, as I said, not this problem of slow Kolmogorov with decay affects not only advection-dominated problems, but a lot of applications. Like, for example, problems with the parameterization that change the computational domain, or more complex models with complex dynamics and smaller scales in your dynamics, etc. So a lot in the literature, these are some references, some methodologies with which researchers have tried to solve this problem. So and some of them can grouped as local methodologies like domain decomposition or interpolation on the space of parameters. Some others take inspirations from machine learning, nonlinear dimension reduction techniques like kernel-based methods. Some others from imaging sciences, like old techniques like registration, applied, for example, in 2014 for registering geometries. And more recently, also autoencoders, so in the last reference of Lee and Carberg. And today I'm going to talk about an extension of their methodology with hyperreduction. So autoencoders have been have spread also in the model reduction community and surrogate modeling community. Also, thanks to the advent of ResNet and CNNs from the 2010 to 2015-16, and also with the development of open source software like PyTorch and TensorFlow available for everybody. And especially these are some of the first works I managed to find on autoencoder and as well as CNNs used as purely data-driven methods in computational fluid dynamics. So a lot of techniques also nowadays are structured like this. So they are purely data-driven runs, and they have the task of surrogate modeling is divided in 2 steps, let's say, even if sometimes they perform at the same time. So the first step is to approximate the solution manifold. And so the basically architecture you have is an autoencoder. So with an encoder map C from the full state dimension to a reduced latent dimension R, and the decoder map from the reduced latent dimension R to the full state D. And then you have another lecture that whose job is to infer and to learn the latent dynamics of your system. So if you plug in different parameters, for example, also time, and you predict the solution, but inside this smaller latent space. Of course, in the literature, there are many examples in which the architecture changes. So, for example, you can use for the solution manifold learning problem, convolutional autoencoder, variational autoencoders, GANs, adversarial autoencoders, LSTM autoencoder, CNNs, Bayesian autoencoder. There are many architecture available right now. And also for the latent dynamics, you can use Gaussian process regression, feed-forward neural network, LSTM, causal convolutional networks, narrow Ds. There are many alternatives. But these are only pure data-driven methods. So this means that there isn't a training stage and a predictive phase, but in the predictive phase, you only plug in your inputs, your parameters, so for example, time and other parameters of your parametric PDE, and get the solution. Instead, what you wanted to do is to preserve, in a sense, the physics. So instead of using this paradigm, we wanted to find the solution also at the line stage, in a sense, solving keeping in mind the numerical scheme using the full order model. So, for example, minimizing first principles. And this is something that you cannot do with standard data-driven ROMs that discard completely the physics in the predictive phase. So the original work introduced by Lee and Carberg can be presented like this. So you first discretize your parametricity in space and you obtain NOD. So in this case, you represent your state variables. So the physical field can be stuck together. For example, for the incompressible Navier-Stokes equations, you would have a velocity and pressure, and you would then obtain an NOD system, where F is your vector field and can be also nonlinear depending on your PD, and of course the initial condition. And you can discretize it in time, and in this way you have a residual that depends on the parameter, of course, but also on the time instant you are solving for the solution, and also the previous time instances belonging to the interval IT, and the discretization of the initial condition. For example, for the implicit Euler method, you would have a formulation of the residual like this one. So this is the boxes compare the least square Petrov-Galerkin method, it's an application of this basis, with the nonlinear manifold SPG, and you can see the difference is a lot on the choice of answer space. So on the least square Petrov-Galerkin method, you start from a latent a reduced coordinate Z0 that you obtain after a linear projection of your initial condition U0, and this PR matrix is just the matrix whose column are the eigenmodes of your SVD, for example, of your snapshot matrix. So what you do next is, if you have time and parameter, you have to find the solution at the next time step, solving these least square problems. So I'm minimizing the residual. And in this case, instead of the state UTH, you plug in the reconstruction from the latent variables PRZ. Of course, if your PDE has an affine decomposition with respect to the parameters, you can save the reduced matrices offline, and the procedure will be efficient. But if your residual, for example, is nonlinear, then you would need to apply hyperreduction techniques to make it solving this problem independent from the number of degrees of freedom. So on the right side instead, you see that using encoder and decoder, so nonlinear maps, is easy as just plugging in them inside the position of the state you would be considered before. And so now to find the initial reduced variable, you would use the encoder and encode the initial conditions, and then you would evolve the dynamic in the latent space, always with a small dimensionality R. But in this case, the state would be reconstructed from the latent space to the full state space through the decoder phi. And so this is the formulation. If you want to think about it graphically, you have on the left side a plane, which is our vector space spanned by the eigenmodes of SVD that approximates this kind of nonlinear manifold, while you can see that dynamics is evolved in the latent space and only in the end reconstructed on the solution manifold. While on the right, you want to try to approximate your solution manifold with a nonlinear approximant map. So in the end, you will also have a nonlinear approximation of your solution manifold. Of course, now, if your residual is in the beginning linear, you introduce nonlinear maps, so you will need to solve a nonlinear least square problem. If your residual is nonlinear, it would still be nonlinear, but you add an additional nonlinearity coming from the decoder. And there are many methodologies that can be used to, optimization algorithms can be used to solve the nonlinear square problem, among them quasi-Newton methods, and also other variants like pounders implemented in PETSI that is what we use for the benchmark I present today, but also the Levenberg-Markov algorithm that I've tested for other benchmarks in other references from inside the Eigen library. Of course, the problem is that, as in the original implementation of Lee and Carberg, you still have a dependency on the full dimensionality of your state space. And so even with this formulation, it may happen that your Düsseldorf model is even more inefficient than your full order model. So you need to apply some sort of hyper-reduction. And of course, the full dimensionality, I mean, the residual has full dimensionality, but also the state space. And one of the simplest approaches is to use overcollocation method. So you define a matrix which restricts the residual only on some collocation nodes. And of course, if you consider standard methods like DG, FEM, or finite volumes, then if you want to evaluate the residual locally on single nodes, you would need just a stencil around them because the differential operators of your discretization are defined only locally. And of course, these maps pass inside the residual definition, and what you just need to do is restrict the reconstructed state space only on this submesh PSRH. And in the end, so you can restrict the residual G tilde only on the collocation nodes and the output of the decoder only on the submesh. Of course, there are many other implementations of production. There is DIME, there is ECSW, there is GNAT, there is also SOPT, which improve the point selection algorithm. And yeah, but of course, I will show maybe some examples of these submeshes if it's the first time you've seen it. So in red, you see the collocation nodes, so only the nodes in which the residual is evaluated. And in blue, in light blue, the nodes, the cells that are used that make part of the submesh. So on these two grids, orthogonal grids, come from two benchmarks that I've used in another experiment. I'll introduce it later maybe. But you can see that this is a nonlinear conservation law problem with the parameters also time. So you can see a moving front from the left bottom corner to the right top corner, and this is the shallow water equation. The solution should have a radial symmetry. But you can see that the submesh size depends on the numerical scheme you're using. So for example, you could have only one layer around each single node of your residual or more layers around them. But of course, the problem is that now you use a decoder, which in general may be a very big map. And so you need to find also ways to or define shallow or thin architectures that are at the same time shallow and so efficient to evaluate many times and accurate, or you have to find other techniques to solve this problem. So these are the references I could find about extensions of the nonlinear manifold method, and all of them use hyper-reduction in a way. So the first reference was, of course, by Kim Yongsoo et al. Where they used the shallow mask autoencoders. We attempted to use convolutional autoencoder and then approximate the decoder with a smaller one in a second step with teacher student training. So it's a paradigm in machine learning to train smaller networks from bigger models, let's say, so that we could have an efficient small network to use in our nonlinear optimization to solve the nonlinear square problem. But there are also other approaches in the literature that consider, for example, autoencoders between submeshes of hyper-reduction, or that split your nonlinear approximate in a linear part and the linear part, but obtain also composition with a nonlinear part made of a neural network, or an approach that I'm going to present today. And also, of course, approaches that consider partitioning approaches. So the composition in each the composition of a domain, you consider a new autoencoder and perform in this way hyper-reduction. And so the approach I'm going to talk about today is the following. It relies a lot on a technique very well spread in machine learning, which is it's considered using SVD as per processing step to extract meaningful features from your database. For example, if you have in mind the diffusion processes and stable diffusion, so diffusion model and stable diffusion. So what you do as per processing step, you extract and reduce the dimensionality of your image, let's say, usually with other architectures, but you can also do, or in this case, we use SVD, or more generally, I call the filtering transform map. And with this, I mean parallel randomized SVD, which is very efficient for very big problems on meshes of more than 1 million degrees of freedom. But you can also consider a fast Fourier transform or other transform of your choice. So the architecture is instead, in this case, done is as the structure. So you first have a linear layer that you consider, let's say, a matrix with columns, the eigenmodes of your transform map. For example, the eigenmodes of randomized SVD, and that projects your state space from D to a dimensionality P, the dimensionality of the frequency space, let's call it. And then from you want to reconstruct this frequency space with a small autoencoder made of feed-forward neural networks or 1D CNNs. And so this autoencoder maps this frequency space P to a reduced latent dimensionality R, and then reconstruct it back with phi tilde and decoder from R to P, where P is much smaller than D. So P would be the number of your reduced basis modes, for example. But with respect to reduced basis applications, this P can be much higher. So usually for reduced basis can be less than 50 modes, let's say. In our applications, P is equal to 300. Because it achieves an accuracy in a very efficient way with randomized SVD in this way regarding the reconstruction error. And finally, we have a linear projection from P to the full state space D dimensionality. Of course, if you consider U as a field UH, you consider many fields stuck together, and we applied a monolithic SVD, and of course have to renormalize the fields because you may have pressure and velocity or other fields, and so you need to apply a weight that let's say make it this state space independent from the unit of measure and of the on the physical quantity you are considering, let's say. In this way, you obtain a more accurate reconstruction error, considering only randomized SVD. So now you have, let's repeat, a very small and fast to evaluate decoder from R to P, because it's just from the latent space to the frequency space. So the space of the, that you obtain projecting your snapshot, and then you have a linear projection f-1 filter from this frequency space P to the full dimensionality. And why this choice of architecture is very useful for our applications, because then you can apply hyper reduction very efficiently, because you have a very fast network to evaluate, and then you can, if you want to apply hyper reduction and you have selected the submesh, then what you need to do is just restrict the rows which represent the DOFs of your system. You can just erase them if they do not belong to your submesh, and what you find then is just this nonlinear approximant composed by a nonlinear part, which is the same, the decoder part of your autoencoder, and then a much smaller linear map from the frequency space P to the restriction of your modes to the submesh you are considering with your rapid reduction technique. In our case, the overcollocation method. So in this way, you have found an accurate, in some cases, when randomized SVD achieves a good reconstruction error, using also a lot of modes, like 300 modes, but also thin, because you restrict the linear map, which is the biggest part of your network, only to of your map of your altogether nonlinear map, only to the submesh. And we wanted to take a step further, and we wanted to also try an adaptive strategy, since when you consider hyper reduction, sometimes if you have a fixed mesh, but then the major components of your residual moves during the evolution of the dynamics. So you may want to follow these features of the dynamics with your magic points. And so one way to do this, consider also that we have a nonlinear map that uses in our network, is the following. So you first define a map from Z, which are your latent variables, to the residual state space. So Z is mapped to reconstruct the state space with the phi, which I want to remark is made by a phi tilde, which is a nonlinear part and then a linear part. And then this is plugged into the residual evaluation, and that has the full dimensionality of your state space. So then you want to compute sensitivities. So it's simple chain rule. You see that there is a component that is the derivative of the residual with respect to the state, a component that's linear with respect to the reconstruction, with linear reconstruction we are employing, and then a component which is the Jacobian of the output of your restricted decoder, of your, small nonlinear decoder, with respect to the latent variables. So in the end, to evaluate these sensitivities for the choice of magic points would be too much expensive. And so we decided instead to use this kind of indicator. So we cut off this part and we consider only this part here, which instead considers only the reconstruction filter and the previous latent coordinates to evaluate the Jacobian of phi tilde. And so in this way, you have a map which is more efficient to evaluate, but as a dimensionality from the latent space R to a matrix D, which is the dimensionality of the state space times R. Of course, if you do want to, of course, this depends on the full number of degrees of freedom, but if you want to reduce further dimensionality, you could consider to restrict this evaluation only to, let's say, a neighbor with a neighbor of your actual submesh to make it the procedure more efficient and fully independent with respect to the number of degrees of freedom. But for simplicity, we consider the full state space. And so now you can minimize, of course, you have to compute since your state space has many can have physical fields. So like, for example, a number of C physical fields, like, I don't know, pressure and velocity, you have to take the L2 norm with respect to that. Then you take the R max with respect, so you choose the most influential latent variable. And then you decide which are the cells of your mesh. We are considering infinite value method, cells of the mesh, which would correspond to the magic points in which this quantity, this indicator, has its maximum value. Okay, so this, for example, you would have this kind of submeshes that evolve with the dynamics in the case of compressible flow past the NACA airfoil. And you can see in black the magic points and in gray the submesh around them. And you can see that more or less follows some important features of the dynamics from time step 0 to time step 2 seconds. We also wanted to point out another important characteristic of the choice of our nonlinear approximant, which is the possibility to use a local formulation. Because now, for example, if you have time as parameter, as I will show later, you could, for example, split the time interval in two and decide to use one linear basis for one sub interval of the time interval and one sub basis for the other time interval. Why this procedure is still efficient? Because then you would offline you would have two autoencoders, so one for sub time interval, and then online you would just you can just multiply the linear basis, and online you would just perform this cheap change of basis between P1 and P2, let's say, the dimensionality of your frequency space. Of course, this is a very simple and maybe naive way to perform let's say the projection from one local linear approximation to one other local linear approximation. In the literature, there are many work that make this procedure more rigorous and take into account other interface conditions. But this is a very simple way, and we wanted to point it out because it could be used with our approach if you really wanted to use a local linear approximation of your parameter space. And so the first test case I'm going to consider is a compressible flow Massanak airfoil. And the parameter we consider here are time and the inlet Mach number. So we choose the molar mass of our gas such that the speed of sound is equal to 1. And in this way, we can choose the Mach number as parameter and set it as the choice of our inlet velocity from 2 to 5 in the training range, and from 1.8 to 5.2 in our test range. So just to give you a grasp of the solution manifold we are considering for the initial, for close to the initial time steps, 0.2 seconds. So the first and third snapshot with Mach number 5.2 and 1.8. These are all in the extrapolation regime. So these are, let's say, the extremal solutions. But you see, it's very big, the solution manifold we want to approximate. And this is implemented, the solution are obtained with the finite volume method in OpenFOAM with the sonic foam solver. So if you look into the sonic form solver and compare it to our implementation of the nonlinear manifold method, you see there are some differences. In fact, the sonic form solver, first of all, the fields we are considering are the velocity, the density field, the internal energy, and the pressure field. And the sonic form solver consider a predictor corrector numerical scheme inside it. And also you consider a non-orthogonal corrector because when you have also, as in this case, non-orthogonal meshes. But instead, in the nonlinear manifold method, for each evaluation of the residual, we don't need to use this predictor corrector scheme, but instead inside the nonlinear least square optimization, at each evaluation of the residual, so at each n time step, but also if step of the optimization, we can evaluate just the residual in this way, so without using the full scheme, let's say. And also, of course, remember that we only evaluate the residual on the submesh. Okay, so these are some predicted solutions for a qualitative comparison, and this is what. Okay, it takes some time. Okay, as you can see, okay, this is the full evolution of the submesh. And so in this case, we have considered for this test case 20 training parameters as Mach number and 5 test parameters. And the test case I'm showing you, the snapshots I'm showing you correspond to the Mach number 2.124. As I mentioned in the beginning, I consider as the dimensionality of your linear projection. So P is equals to 300. So we use 300 RSVD modes, something that maybe you wouldn't do with the reduced basis method. And we consider a latent dimensionality of R equal to 4. These numbers are chosen only to achieve a good accuracy with the wall reconstruction, for the wall reconstruction error. So in this case, we have used 1,200 adaptive protection collocation nodes. And they are updated not every time step, but only every 20 time steps. Of course, the choice of when to update them can be maybe worked out better with, I don't know, maybe a posteriori techniques. And remember that we are comparing the computational cost with the open form solver. And in this case, if you consider mean time step, we achieve not much of a speed up, less than 2, but you see that 74 milliseconds for evaluation for a single time step at the nonlinear manifold method is quite the standard of also if you consider other works in the literature. The thing is that now we compare with the full order model made implemented in open form, so a very high performance solver for a very simple problem with just 32,000 cells. But with our methodology, we also try to increase the time step, so that would incur in problems for the CFL condition at the form level. So we could use a time step also, which is 4 times higher. And in this case, we do achieve a speed up of 5 for evaluating the full dynamics in this simple test case. And I show also some results on the true relative error for the local nonlinear manifold application. So as I told you, we consider true time intervals from 0 to 1.2 and from 0.6 to 2.5. And we consider 2 different RSVD modes for these 2 time intervals and also autoencoders. And we compare what are the errors with the use of these 2 subintervals or with the use of 1 single subdomain. So in red, 1 single subdomain, and in blue, 2 time intervals. Of course, in with the yellow line, we consider 5 trajectories are plotted all together, and they are divided by these gray columns. And in red, in shaded red, there is the extrapolation regime, which the solution has very bad errors. And instead, when inside the training regime, inside the training range, you'll see a yellow vertical line. That is when you perform the change of basis from one sub-interval to the other, and the change is performed at time 0.625, if I remember correctly. And you can see that in our case, you cannot get better approximations also with choice of local linear manifolds, but maybe it's still good to point out that you could do it in practice. So the second test case is instead runs around the Ahmed body. So we consider the incompressible Amisto's equations with the turbulence model. So this Almaraz one equation turbulence model. The state we consider in this case are the velocity, the pressure, and also the eddy viscosity. So the turbulence model is cut off in the end when you consider the nonlinear manifold method. So the domain is like this, and you consider 200,000 cells. And this test case has been first considered for in model reduction. Well, not in model reduction community, but my collaborators have been worked on this test case previously, but they consider a stationary test case. So they solve the equations with a simple algorithm. Instead, we'll try to predict the transient dynamics with the piezo algorithm in OpenFOAM, piezo solver in OpenFOAM. So the parameter in this case are time from 0 to 0.1 seconds and the slant angle of the Ahmed body. We consider two parametric instances, two parametric ranges. The first parametric range is from 15 degrees to a bit more than 18 degrees, and the other parametric range is higher, from 15 to 35. And we'll see what could go wrong with this methodology. So these are the, maybe I can share again the presentation. Okay, so these are again the evolution. This is again the evolution of the submesh. And in this case, we consider only 5 train parameters and 4 test parameters. And I'll show you this is the predicted solution for slant angle equal to this value. And of course, in this case, I repeat, there you want to predict velocity, pressure, and you also predict the viscosity. And also in this case, we consider P equal to, so the number of your RSVD modes are 300 and the dimensionality of 4. Again, these numbers are kept fixed also in this case, but just because we could achieve good accuracy with respect to the extraction error. So maybe they are not an optimal value you would choose. You may perform some parametric studies to find a slower, maybe on a higher, if you want to achieve a better accuracy, for example. So in this case, the magic points are evaluated every 50 time steps. And in this case, you consider the mean time step, you would achieve a bit of a speed up at least, even if this is still a very coarse mesh in OpenFOAM. So you would achieve at least a speed up of 5 if you consider only the mean time step. But also in this case, we consider an higher time step with respect to the FOAM because we could do it at the reduced level. And in this case, if you consider the full dynamics, instead you attain a speed up of 26. Of course, maybe you don't see all the submesh because a big part of the dynamics, so the highest values of the residual are evaluated below the Ahmed body. So the stills, around the stills, there are the, it's similarly flow past the cylinder flow, let's say. And so you can see that the residual, and also the submesh follow these features below the Ahmed body. And this is also for the pressure. For some more quantitative estimates, you can see that the pressure and velocity are quite good approximated for this test case. Instead of the eddy viscosity, you have much worse approximations, also because it's more difficult to linearly approximate it in this case. But of course, I want to remind you that this is a monolithic SVD. So in a way, the pressure, velocity, and the viscosity are coupled in a single eigenmode. And of course, this is still the parametric domain range from 15 degrees to a bit more than 18 degrees of the slant angle. Instead, if you want to consider as parameter range from 15 to 35, there would be some problems. And this happens not only for this implementation of the nonlinear manifold method, but also generally for applications that consider also pure data-driven methods that consider SVD as per processing step, and then a nonlinear autoencoder. And then maybe they learn the dynamics with another network. This is because for example, if you see there are 13 parameters. So the first plot at the top, there is the abscissa corresponds to different parametric instances of the slant angle of the embedded body. So we have divided this interval in 50 parts, and each parameter, you can see 13 training snapshots, and the colors represent the choice of RSVD modes used to evaluate the reconstruction error. So this is the train L2 relative error, and this is the test L2 relative error. And you can see that if you increase the number of modes, there is a parametric subinterval for which you cannot achieve a good accuracy, even increasing the number of modes. And this is very typical for a lot of applications for which you need, maybe you think more data, or maybe the linear approximate is not good. Something you could try is to use instead local approximation. So you may want to, let's say, from a sort of clustering of your parameter space and decide, okay, I divide my parameter space into 4 parts, and then apply RSVD in each of the 2 parts, hoping that the reconstruction error would be better in that case. Also, considering that you have also many solutions in that particular subdomain. And for some subparametric, for some sub-intervals of the parametric space, you obtain better approximations, but still not good enough in some ranges of your, in some intervals of your parametric domain. And maybe in these cases, other approaches would be more preferable with respect to the linear approximants. Maybe you may want to try to use much bigger neural network architectures, such CNNs if you have grids of graph neural networks, or more or other architectures. And in this case, so you cannot use the methodology I presented, because you cannot use RSVD as preprocessing step, but you can try to use another approach we have developed before, and this uses teacher student training. So you first train a very big architecture. For example, in this case, for a nonlinear conservation law problem, you train a convolutional autoencoder from a grid to a grid. And then after training it, you can train a smaller decoder that you will use in your nonlinear manifold method. And this decoder is made by just 2 hidden layers, and it's a very simple feed-forward network that is evaluated from the latent coordinates to just the submesh to the states of your training database, but only restricted to the submesh. So you do have then a very smaller network to use for your nonlinear manifold method. And so I briefly summarized the conclusion and possible pros and cons of the methodology. So what we have with respect to data-driven procedures is an interpretable procedure. So it's more explicable as a procedure, because at each time step you are minimizing first principle. So you are minimizing physical quantities. And it's more interpretable with respect to black box approaches, in which you plug in parameters and you get solutions. But at the same time, you can also, as in data-driven methods that use, for example, autoencoders, you can introduce additional inductive biases. So you can add some covariance properties in your network, or you could add also positivity of physical quantities. For example, if you have a density in your state space, you can keep this constraint, for example, with the Rayleigh activation function, or also impose other constraints like a weakly symplectic autoencoder. One additional guarantee, theoretical guarantee that you can add with this methodology with respect to data-driven methodologies is the possibility to introduce also structure preservation. So with this formulation, let's say you could also try to implement additional constraint, because every time you don't only evaluate a network, but you also minimize solving a linearly square problem. So you may want to try adding energy conserving property or entropy stable property for nonlinear conservation laws. Of course, there are some cons, and one of them is the possible slow training time. Maybe if the RSVD approximation error is good, maybe then this is not the case, because the training takes less than 1 hour, also with one single GPU. But if you consider, for example, CNNs for a very simple problem like the one I shown before for the nonlinear conservation law in a grid, you can take, if you consider convolutional encoder, even more than 5 hours sometimes to achieve a good accuracy. So possible solutions are represented by transfer learning, or others by partition approaches. And of course, another concept that you may require a large database of snapshots to achieve a higher accuracy. It's very difficult to achieve a very good accuracy with autoencoders when you have a very difficult PD model, when your solution presents a lot of small scale features that you want to approximate. And so this is a very difficult problem to obtain more accurate, and for our implementation, small architectures, because you need them to solve for this nonlinear square problem. And of course, there is the problem of hyperreduction that sometimes is not very robust. So you may want to work on the robustness of the nonlinear square methodology itself, and including how hyperreduction is performed. And maybe approaches include regularization, for example. So these are the references of our works, and I used as open source software Itecafini Volume, the model reduction library developed for OpenFOAM, and Python, Patsy, and of course OpenFOAM. So thank you for your attention, and these are the references I already shown you before.
Thank you so much for the wonderful talk, Francesco. Very nice. Let's have a Q&A sessions. If you have questions, please unmute yourself and ask questions to Francesco. While you guys are thinking about it, let me start to ask some questions. So let's okay. So I mean, you talked about the teacher-student approach in slide 26, but before that, the majority of times you spend on, you know, the specific kind of the hyperreductions where it has a combination of the linear map. I'm assuming the linear map is from SVD type of
yes, exactly.
map. Okay, so the main idea is you apply the SVD and reduce the dimension a bit, and then apply the deep convolutional or some sort of the neural net architecture to further reduce it.
Yes, exactly. The approach I presented today is not on teacher-student training, but on this kind of nonlinear approximant, where in the end, you have a nonlinear part with a nonlinear 1D CNN layers in our case, and then a linear map from the frequency space to in this case, the submesh. And it can be done efficiently because you can restrict your RSVD modes only on the DOFs you need for the submesh. Right.
So my question regarding to that is, as you elaborate the motivation for the nonlinear manifold reduced order model, problem with the Kolmogorov with decaying slowly, like for example, consider the pure convections, right? Like one of the pulse is moving from left to the right.
Yes.
As we all know, for that kind of problem, because the solution snapshots are linearly independent, most of the you need a lot of SVD modes, right?
Yeah.
And this approach, since you are combining linear SVD, linear map with a neural map, nonlinear mapping, isn't it kind of limited to how much the SVD can compress your original data? And if the data is coming from pure advections, for example, then you pretty much like almost like the full space or full space snapshots, number of snapshots. So yeah. So
yes.
Can you comment on?
Yes, that's true. It's true, but maybe oftentimes you don't need to. I mean, we actually use a very high number of modes. I mean, not very high, but 300 is high. And usually you have this Kolmogorov decay problem asymptotically. So for some applications, you may still use a limited number of RSVD modes and achieve a satisfactory accuracy. Also because, let's say, the linear advection case of is like an extremal case with respect to some applications. But some other examples of problems, real problems where this approach works, also only data-driven problem, so or where only data-driven approach is tested, can be found on the works of Stefania Fresca and Mazzoni, where they extensively tested their POD-DL-ROM technique, and they've shown that also for some electrophysiology test cases, you may still, with less than 300 modes, approximate dynamics, which is advection dominated. So it really depends on the accuracy you want to achieve. And of course, when you get problems like the one I've shown at the end. So in this case, so when you have, also here, I would say that you have this problem. So when you cannot approximate well the solution manifold with just linear modes, then you would really need to use a nonlinear dimensional reduction technique. So yes, the approach I presented works in an intermediate regime, let's say, where when you need to use more modes than the number of modes you would use for a standard reduced basis methods, but still not too many, and so for you not to require nonlinear dimensional reduction techniques.
Great. My second question is about the adaptive hyperreductions, and there you are changing a list of magic points every like 20 or 50 iterations.
Yes.
And once you change the magic points, only the hyperreductions on the linear map is you have to update it online.
Yes.
I guess.
Yes, exactly.
But you don't change anything on the nonlinear map.
Yes.
Part.
Yes.
Okay.
Correct.
Okay. Cool.
Yeah.
Even there, like updating the linear map hyperreduction informations, that takes some computational time. I guess that's why the average time step cost is high for the.
Yeah, but in this case, we use only reduce over collocation. So restricting the modes to just the submesh, to a different submesh, is very efficient. No, I guess the cost really depends on the number of iterations of your optimization scheme with which optimization method that you use to solve the nonlinear square problem. And
Okay.
of course, this is, I don't know if in your experience, but yeah, it's difficult to get under this value. Also in our implementation, maybe it's not as efficient as the code in which they implemented the numerical solvers of OpenFOAM, since we blended, let's say, Python with the residual validation in C++ inside OpenFOAM. And yeah, maybe a more efficient implementation could be performed.
Could help.
But, yeah, but sorry?
The efficient implementation could help.
Yeah, maybe so. Yeah, maybe implementing everything in C++ or yeah, I cannot think of. Yeah. But maybe in your experience, I mean, may not be much different with respect to your single iteration of your shallow masked autoencoders. So maybe it's really the comparison with the OpenFOAM solvers in these very coarse problems that.
Yeah, in some sense, it's not a.
point.
In some sense, you're not comparing apple to apple. I guess.
Yeah.
OpenFOAM is a C++, and your implementation is on what, Python?
Yeah, but we evaluate the residual efficiently in C++, but let's say the NACA is on Python, so also the optimization with PETSI, but PETSI for Pi.
Okay. Okay. All
to
right.
make it simple to test different techniques. Yes.
I see. Oh, okay. In that sense, there's some room for improvements.
Yeah.
Yes. Okay. I have one more question if you have time.
Yeah, sure.
I really kind of wanted to see the more about the teacher-student approach. So am I doing it correct? Like the slide 26? Because I thought that was really a kind of killer. Killer approach in nonlinear manifold reducible model in general, because you do not have to relying on that linear map, and and you can fully take advantage of the expressibility of the the neural network, the nonlinear map neural network. Yeah, what kind of speed up do you get if you apply this teacher-student training?
I remember that in those cases, I remember, actually the grids are the ones I've shown for reproduction here. So we tested it on a nonlinear conservation law and on the shallow water equations.
Yeah.
And the grid was, I guess, 60 by 60. So it's very small problems solved in open form. And also in this case, I guess we could not achieve a speed up. I mean, we matched the mean time step for the nonlinear conservation, and we managed to achieve a speed up of 2 for the shallow water equations with the implementation of the teacher-student training network. And in that case, also we computed also the Jacobian in a very efficient manner because we had only a 2-layer network, so we could evaluate it efficiently. Yeah.
Oh, okay. Yeah. And your full order model was still open form?
Yeah, it was still open form. Yeah.
Okay. Well, thank you. Is there any other questions? It's past 11, so. Well, thank you so much, Francesco.
Okay.
It was wonderful. And I learned a lot. So that is great. Yeah, if anyone has any questions for Francesco, please reach out to him directly. I'm sure he's going to be happy to get any questions from you guys.
Yeah, definitely.
Well, thank you, Francesco.
Thank you. Bye. Have a good day.
Bye. Francesco.